Hi, my name is Mark Knutson. Welcome back. This is the third of 5 videos. We've been looking at baseband link control from Matlab Cockpit of SystemVue to take advantage of all of the nonlinear impairments. And we've already covered the shipping example in video 1. We looked at how to troubleshoot any errors that might pop up, and how to really make sure you've set everything up and get the expected results in the last video. In the third video, we're going to dig a little deeper. We're going to look at a data flow simulation that happens to do beamforming, but for all intents and purposes, don't let that worry you if you're not doing beamforming. It's a data flow simulation. So a lot of the same things we're going to talk about, you can apply. And we're going to look at 3 different versions of that. But this video number 3, is a case where we're going to generate a modulated source from Matlab. We're going to tune the beam. So it's a kind of a dynamic data flow simulation. We're going to get on the far field spectrum, we're going to capture that live, put it back into Matlab, into the sync. And we're going to also grab the antenna pattern just as a post-process gain theta phi from SystemVue. And so we're going to show how that works. Before we get to the demo here, we talked about in the first video kind of the difference between SpectraSys subcircuit RF link running on data flow. You should know that standalone data flow, if you place a phase array architect design, which is basically a matrixized version of SpectraSys for phase array design, if you drag that onto a data flow, it'll create something called an RF link phased array. This runs no problem standalone in SystemVue. However, it's not supported for baseband link yet. The reason for that is they need to update put a cache like is in the RF link for the behavioral model, and that keeps track of the behavioral model, frequency domain model in the data flow simulation. They need to add the same thing in the RF link phase array. The SystemVue development team is planning on adding that in an upcoming release. But so just know right now you can run standalone, but from baseband link, it's not supported. But there is an easy workaround, and that's to use data flow parts for beamforming. So the matrixized splitter, the phase shifter, and the amplifier to do tapering. And you can control the beam theta phi. There's a lot of, you can do the exact same thing in pure data flow and not using RF link phased array. That'll be coming. All right, so the first example is, sorry, it's not the first example. We're on the third video. The third video is based upon this example here. It's again this link here, and if you look at that in Knowledge Center, you can download everything that we're going to show here, and it walks you through step by step what's going on. So let's have that loaded up. And this is the first example, beamforming example. If we put run from Matlab to 1, as you remember in the first video, that basically controls what when you run it from Matlab, what baseband link is seeing and controlling. And so like, for example, that's set by the baseband link source here. If we go under equation controlled and do control by equation, it's set from run from Matlab. Or it could just be always on, use the active model. But in this case, it's controlled by an equation. And that's why when you change this from 0 to 1, what you see is the source switches from the 16-QAM built-in SystemVue source and uses Matlab's going to generate the 16-QAM signal in this case. And the other thing that is active when you go from 0 to 1 is the baseband link sync, and that's coming at the far field after the antenna. Antenna array TX generates the far field beam. It's measuring that spectrum. So let's look at the rest of the design, just make sure we understand what's going on. But you're going to generate the 16 QEM signal from Matlab. You're going to do the beamforming. So you're going to go through a splitter, in this case an 8x8 splitter. You're going to do phase shifting and tapering amplification that's controlled by beam theta, beam phi, and the beamformer weights part in data flow. And you're going to basically use a part called antenna array TX, generate the far field beam. You could control the channel with noise density if you want, and then you're going to measure that beam. That's going to go to Matlab, and Matlab's going to have that far field spectrum. The other thing we do in data flow is we generate the beam pattern, render the beam using the beam pattern part, and that I'm going to save off the antenna gain theta phi, so I could do a beam pattern from the results of my simulation. So I've got a Matlab source to generate the modulated signal. I've got a Matlab baseband link sync to take the data, the far field spectrum, and use that in Matlab. But I'm also using some syncs in the SystemVue simulation, antenna gain, theta grid, and phi grid, and I'm going to capture those from an ADX file post-simulation and plot those. In SystemVue, it's very easy to plot a beam. So right now we have the beam theta set to 30 and 30 degrees. And if we run this simulation, actually, let me turn it back to, I'm going to run it internally just in SystemVue. If we run this simulation, runs pretty fast. Get the beam at the output over here. And it's a few lines of code to basically take those output theta phi gain of my antenna, and I can plot a beam pattern using these few lines of code. Squeeze functions used because if you look at the data set, if I look at like the phi grid, it's a 1 by 361 by 181. That's kind of an index that we don't need, so I'm using the squeeze command to get rid of that. And so the plot patterns to equation in SystemVue, that's why I use the squeeze command. And then I use a graph to graph the spherical data. And so here's what happens if I right click and I say run equations. It generates the beam. This was done at 30 degrees theta. And here's the resulting beam. Let's say markers, peak. I can see that's at 30 degrees theta. So that's what's going on there. And I can also basically look at the directivity plot. So I see that's at 30. Let's compare that to what we get in Matlab. So if we run this simulation, actually I have this over here in the example. So if you run this simulation if you do the if you set beam 30 and you run that simulation, you run that from Matlab, and if you hit run in Matlab, if you have beam theta 30 on line 8, the directivity looks like this, minus 30. This is in Matlab, and this is what I'm seeing in SystemVue. So it's getting the data directly from SystemVue. So you can also check the phi matrix and the theta matrix. All right, so that's what's going on there. let's take a look at before we do a 45-degree case, let's look at the code and see how it's set up to do this in Matlab. So in Matlab, if you I have it here on the Knowledge Center example, but it's also, if you can follow along in the Matlab code. But basically, line 2, we do config.getVersion. That's just a troubleshooting, good kind of practice to let us know what version of the SystemVue engine we're running. We set the cardinal parameters in lines 6 through 8, and we remember we're generating the 16-QEM signal in Matlab, so we do all the root raised cosine filtering. Line 24 is X, or sorry, line 29 is called, creates a variable called X, which is the 16-QEM modulated created from Matlab, and basically it's a precise number of blocks that we've created, and then we open the workspace with line 41, and we DF1 is the data flow analysis controller for the 16 for this beamforming example. You can see that here. DF1 is controlling design 1, which we're looking at, and we set the carrier frequency, sample rate. Again, these are all at the schematic level, passed in as parameters. That's important. And if you have any equations, you got to do those here. You don't do those externally. And by the way, I talked about the plot patterns earlier. You notice this has a tilde A. That means that the auto calculate's turned off. You don't really want to use auto calculate when you're running remotely from Matlab through baseband link. I would recommend turning that off. And and not using workspace level Matlab equation blocks, but defining things at the schematic level. So that's why I have equations here to calculate like the phase array geometry and phi cut angle and that kind of thing, center frequency, and we pass in parameters from the schematic level also. Okay, so let's finish looking at the code. So if you go down to line 51 of the Matlab script, we define a container, and source and sink, line 59, line 60. That line 59 and 60, let me put this back on, run from Matlab. So the from Matlab source is what's called in the code here. And line 59 from Matlab, it's that instance, points to that instance of the baseband link source. It's called source is going to reference that. Sync to Matlab FF far field spectrum. That is on the other side. And that's to Matlab FF spect. And that's what's referenced here. We start the simulation. We have a precise number of, we do a for loop and basically use the source use the get set data under that to feed it the 16-QEM samples start index to stop index that we created in Matlab, and then we capture the output of the SystemVue simulation, start index to stop index precise number from the sync1 get data. We stop the simulation, close the workspace, and then we do a plot capturing at this point, capturing the voltage spectra, and that's what generates this plot in, and so that's been done before in the other videos. If you wanted to, just a comment, you can run this simulation in SystemVue. You could turn on, there's some dynamic parts like the 3D beam measurement part. I can activate this, but I wouldn't run this when baseband links in running things. It'll tell you it's not supported. So I'm going to just run this and show you what it does. But I'm going to activate this. If I run this, it's going to give me the spectrum, and it's going to give me the spectrum. And what it also gives me is it does some beam measurements. So I'm going to measure like the phi cut, those kind of things. So now I have the fight cut of the plot, and I have the power. So those are some of the nice dynamic features that SystemVue has when you're running a standalone, but you don't want to use a dynamic part like this measure the beam part when you're doing baseband length because it's running from Matlab. So you can deactivate that as I did. And I guess last but not least, let's take a look at what happens when we change to, this is what it looks like at 30. We looked at this when we set theta 30 degrees. What happens when we set theta to 45 degrees? So I'm going to change theta to 45 here. And if I run this, this is what it looks like in SystemVue standalone. I guess I can stop it. And basically can delete this plot. I can run the patterns again. We looked at that before. And now if I add a peak marker, it's going to show the 45 degrees theta as expected. So let's compare the directivity. Now it's minus 12, minus 10, as you can see, to see what we get from Matlab. So if I bring up the directivity, which is created at the end, right? So it's post-processed. We take the ADX file from running the simulation remotely from Matlab. We capture the gain grid, the theta phi grid, and then the gain grid, and basically put those into phi matrix, theta matrix directivity, use the squeeze function like I described before. So if I look at the directivity, click on that, we see that it matches minus 12, and that matches what we see in Matlab, and that's what we see in SystemVue. So hopefully that was helpful to see it in action on our first beamforming example using baseband link. Thanks. See you next time.